So in this video we're going to have a look at the specific trends in this periodic table. Now the periodic table is a tool that chemists can use to understand a little bit more about the specific properties and the structure of elements. Now an element is just a special type of an atom that's been known to have a special number of protons. So all of these are the most basic elements, the most basic building blocks of matter. Now they have different names because you can have an atom, say, with 3 protons inside of it, and therefore it has 3 electrons around it. I'll just draw that. Or you can have an atom, say, with 1, 2, 3, 4 protons in it, and therefore it has 1, 2, 3, 4 electrons in it. Now these both are called atoms. So atoms is the generic name. It's a building block of matter. But the difference between these two is that, well, they're not the same atom because they have different proton numbers. So this is an element, these two are elements. Okay, so the one with 3 protons, if we look at the periodic table, we can see that 3 protons means that it's lithium. And the one with 4 protons, if we have a look at the periodic table, 4 protons indicates that this particular atom is the element beryllium. Okay, so that's how you distinguish between atoms and elements. Elements are specialized because you know the number of protons. Atoms is just a very broad name for little tiny specks of matter. Okay, now let's have a look at the specific trends in the periodic table. I'll just get rid of this, and now the periodic table is not organized in a random way. It's organized in a very specific way. As you go down the column, so say hydrogen, you look at hydrogen, then lithium, then sodium. This is known as a group. And as you go across, this is known as the period. So the periods go down across horizontally. Okay, so you can say that, say, sodium is in the 3rd period, and so is argon. All the way out here, argon is also in the 3rd period. Okay, the groups, we'll have a look at the trends within the groups, and also we'll have a look at what's happening when you go across the period. So groups are they basically are the columns, and we'll have a look at how this changes, what the special feature of a group is, whereas the period goes horizontally. Okay, now we'll have a look at first what happens across the period. Okay, so if we have a look at lithium, let's inspect the 2nd period because it's the 2nd row down, and we'll start off with lithium. Now if you have looked at the video that was made about atoms, elements, and the periodic table, which I do recommend before watching this video, you'll see that lithium, you've got, so let's just draw it out. Now lithium has 2, because it's in the 2nd period, it has 2 electron shells, so 1 and then 2. Now we know already something about how it fills up, how those electron shells fill up. So you've got hydrogen, we've got these two having to fill up first, and then it gets to lithium. So that's the arrangement of electrons. So in the very first shell, there are 2 electrons, so 1, 2. And then in the second shell, to get to the element lithium, you just need 1 more electron there. Now, so that's what happens to lithium. Let's investigate how neon, how to draw out neon, because this will help us understand sort of what's going on across the period. Okay, so neon, it's also located in the same period as lithium. So neon, Ne, that's my nucleus, and then I also draw out 2 electrons. Sorry, 2 electron shells. 1, 2. But neon is further down, okay, than lithium. Lithium is right here. Neon, you still have to fill in and bring in more electrons into the shell. So neon has, of course, the first 2 shells occupied. The first shell occupied with 2 electrons, and then in the second shell, to get up to neon, you actually have to fill the whole thing in. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now if you compare lithium and neon together, you can already tell something about the trend across a period. So when you move across the period from left, from where lithium was, to where neon is, you'll see that that actually fills in more electrons into the atom. So as you go across the period basically fills in more electrons in valence shell, which is, valence shell is just the last shell that is within in the particular atom. Okay, now, so that's across the period. Now, what kind of effect does this have on say the size of the atom? Okay, so if you look at, it's very interesting, if you look at the size of lithium and you look at the size of neon and you actually compare them two, the diameter of neon is actually smaller than and lithium happens to actually be larger. Now this seems very strange. I mean, why would it be that lithium is actually larger of an atom than neon? I mean, neon does have more electrons in it, doesn't it? So the main reason, so I'll first write the trend when you go across the period, and then I'll explain it. So the trend across the period is that atoms or elements, it's better to use elements, but I've already written atoms, get smaller in diameter. Now, the reason why they get smaller is based on something called electrostatic charge. Now, if I just get rid of this innermost symbol, and we know it's lithium, but we also know from previous lectures that it has 3 protons. Okay, now 3p is probably not the best thing to use. I'll actually use, I'll just draw them out actually. 1, 2, 3. So it has 3 protons. Now neon, on the other hand, neon is, if we have a look at the electron, back at the atomic number that it has, neon has 10. Okay, so inside of neon, and this is exactly why I don't draw these out, but I'll get rid of again the symbol of neon. I'll just put in 10 positive charges. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 positive charges. Okay, now what's really interesting is that the reason why neon is smaller is based on the attraction of, remember that the electrons are negatively charged, okay? So they're all negative. Now they can't really jump into the nucleus. They're not going to jump into the nucleus. They are actually, what they're doing is they're pulling towards the center of the nucleus. So in neon, there's greater pulling strength of those electrons to the center of that nucleus. In lithium, lithium, because it's only got one electron in the outer shell, lithium happens to have less electrostatic attraction towards the nuclear core. Okay, so that's the main reason to explain why atoms get smaller in diameter as they go across the period, and this is because due to greater electrostatic attraction. Electrostatic attraction is just when a positive charge attracts to a negative charge. That's essentially what it is, towards the nucleus. So as a result of that, the atoms get smaller in diameter, and that's very important. So you can that's the most significant trend across the period are the two trends of, first of all, when you go across the period, the amount of electrons in the valence shell increases, and the second trend when you go across the period is that the atom actually gets smaller. Now, another thing that happens when you go across the period is that actually atoms or elements, I'll start writing elements, become less metallic. They actually become nonmetals. Now, it is important to understand what metals are, and one of the main properties of a metal, because if you don't know this, then you're not going to you're not going to understand why they become less metallic. Now, let's have a look at what defines a metal. So essentially a metal, okay, metals are found in the periodic table usually on the left-hand side. Well, they're on the left-hand side of the periodic table. So all of these elements here are metallic. You've got the transition metals, which are here, which we're not looking at, and then there is a kind of gap here where some of these elements here are metals and some of them are not metals anymore. Now, what's characteristic of a metal is that a metal actually lets its electrons in the valency shell, it lets them go. Now, this is essentially to stabilize the atom. Now, if we have a look at, say, magnesium. Magnesium is number 12. And I'm going to draw this out. So I need to compare these two actually. Magnesium and Magnesium is number 12, as we can see there. It's in the third period. And let's compare magnesium to, say, something like chlorine. Okay, so number 17. Okay, so they're both in the same period. It's just that, yeah, we'll have a look at their nature. So magnesium has 3 electron shells, as does chlorine. So magnesium is number 12. That's the atomic number. I'm just going to write AN. And I'm also going to compare this to chlorine. Same thing, it has 3 electron shells, which I actually haven't drawn properly. Okay, there we go, and then it has to have 1 more electron shell. So they're in the same period, therefore they have exactly the same number of electron shells. So this is number 17. Okay, and as we know that once we go across, we can see that magnesium has, in its third shell, it has 2 electrons, whereas chlorine has 3, 4, 5, 6, 7. I'm just trying to make it a bit different. So chlorine has 7, whereas magnesium only has 2 in its valence shell. Okay, so let's fill this in. So 1, 2, same as here. These are not different. So you have to fill in the second shell to get to the third one. They're exactly the same. Okay, now magnesium has 2 electrons. 1, 2. Whereas chlorine has 1, 2, 3, 4, 5, 6, 7. So chlorine has more electrons because it's further down the period. Okay, so what you'll find with magnesium, okay, because it has these 2 electron shells, these 2 electrons, whereas chlorine actually has 7 electrons in its very final shell. Okay, now the significance of the fact that chlorine has 7 electrons is that usually the nature of chlorine is it's going to want to extract an electron from the outside environment to try to fill itself in the third shell so that it can become most stable. Because as we know, the noble gases are actually the most stable elements in the periodic table because they're not looking for electrons anymore. Whereas for magnesium, it's actually a lot easier. Instead of trying to pull, 6 more electrons, it's actually more easier for magnesium to lose electrons. So chlorine wants to gain electrons. Okay, gain 1 more electron. Magnesium prefers doing it the other way, prefers losing electrons. Now, when an element wants to lose electrons, it's known as a metal. Okay, metals want to lose electrons. Basically, metals are made up of elements that are losing electrons. That's why they can conduct electricity, because they have, in the structure of a metal, they have billions and billions of electrons just flying by. Okay, and that's what allows electricity to be conducted. Now, with a example like with chlorine, chlorine is referred to as a nonmetal because chlorine doesn't want to let go of all 7 electrons. That's really hard to let go of 7 electrons. It's more efficient to gain 1 extra electron from the outside environment than it is to lose all 7 of those electrons. Okay, so nonmetals can be thought of as elements that gain electrons, whereas metals can be thought as elements that lose electrons. Now, let's have another think about this. So, and let's go back to that statement that I just wrote a moment ago, that as you go across the period from the left-hand side towards the right-hand side, the elements become less metallic. You can see chlorine. Chlorine is further down the period than magnesium, and you can see this in the actual periodic table. Look at the position of magnesium and look at where chlorine is found. Okay, so magnesium is right here, chlorine is right here. Now, we already know from just the previous example that chlorine must be smaller in size than magnesium because it's further down the period, and we know that the electrostatic attraction to the core of the nucleus is actually greater in chlorine compared to magnesium. And we also understand that magnesium wants to let go of its electrons, so it's more metallic, whereas chlorine wants to actually gain electrons. So as you go from left to right, the elements become less metallic or more non-metallic. Okay, so that's another very important concept to understand. Okay, so now let's have a look at a little bit more. So there's a lot of new concepts in this tutorial, so I really recommend that you look over it again and you write notes, adequate notes for this, because this is a very important concept. Now, another way in which we can think of another concept that I want to introduce is something called electronegativity. Now, electronegativity is essentially how much an atom wants electrons. So electronegativity, with respect to the examples that we've just seen, we understand that magnesium compared to chlorine, if you think about magnesium and what we just explained, magnesium is really willing to lose electrons. So magnesium will actually have a low electronegativity. Its desire for electrons is very low. I mean, it doesn't want electrons, it wants to lose electrons. Chlorine, however, has a high electronegativity. So chlorine, because it wants to gain electrons, the strength of pulling electrons from the outside environment towards a chlorine atom is going to be very strong, because it needs that electron to just stabilize itself. So it's going to pull electrons towards itself. So once again, we can create a trend from this. So as we go across a period from left to right, we know something about what the electronegativity is doing. So the next trend that I want to explain is when going across a period from left to right, the electronegativity increases. Metals have low electronegativity, they want to release electrons. Non-metals have high electronegativity, they want to gain electrons. Okay, so finally, ionization strength. So ionization strength is basically, it's also known as the first ionization strength. So when it looks at how willing is an element to let go of its electrons. Okay, so straight away you can see it's kind of the opposite of electronegativity. Ionization strength is related to the willingness of an element to let go of electrons. So you can see that with magnesium, it's very willing to let go of those electrons, whereas chlorine is not very willing to let go of 7 electrons. So if you try to extract an electron out of chlorine, out of the valency shell of a chlorine atom, it's not going to be happy. You're going to have to put in a lot of energy to extract all 7 of those electrons, and it's actually going to get harder and harder and harder to pull them away because there's such a strong electrostatic attraction to the core of the nucleus. On the other hand, with magnesium, it doesn't have a very high ionization. The energy to extract an electron is not high. Okay, so that's another very important concept. Now, as we go, let's have a look at the trends as we go down a group. So we had a look at the period and going across. Now we have to have a look at what happens to our trends as we go down a group. Okay, so we might compare, say, sodium to potassium. Let's have a look at that. Okay, so it's very important to understand how the periodic table is organized and how it affects the atoms, because from this you can kind of begin to appreciate the trends, and they make a bit more sense, hopefully. So down the group. Okay, now as we go down the group, let's compare sodium to potassium. Okay, so sodium, it's in the 3rd period, so it has 3 shells around it, whereas potassium, it's in the 4th period, so it has 4 shells around it. Okay. Now, going back up. So, sodium is number 11 and potassium is number 19. So basically what that means is potassium has 19 electrons around it, whereas 19 protons in it, and sodium has 11 protons in it. Okay, so let's draw the electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the proton number is equal to 11, whereas the proton number here, as we saw from before, is equal to 19, and so we've got 2 being filled here, then 1, 2, 3, 4, that's 10, 11, 12, 13, 14, 15, 16, 17, 18, and then 19. Okay, so sodium and potassium. Now you can see that both of these have the exact same number of electrons in the valence shell. So the valence shell is the very final shell. Okay, and you can see that there's one electron in valence shell. So what this means, because electrons give the chemical properties of elements, they have similar properties. They're arranged in a group. Elements are arranged according to the same number of valence shells, so they have very similar chemical properties. Though if you compare sodium and potassium together, you can see that obviously the size of potassium is greater. Now it's greater because there's one extra electron shell. So as you go down the group, the size or the radius or diameter, whatever the measure is, gets larger. Okay, so progressing down the group means that the size gets larger. Now, another thing that we need to consider, so you're not going to have this sort of difference between metals and non-metals. And the reason why is because, as I mentioned, as you progress down a group, in both cases the elements have exactly the same number of electrons in the final shell. And in this case, sodium and potassium both are considered metals, because again, that one electron can be very easily lost into the external environment. So they do have similar properties. So the size gets larger as you go down a group. Another thing that we need to consider is the electronegativity. So let's have a look at the electronegativity. So remembering that the electronegativity is actually how willing the atom is to accept electrons, to gain electrons. Now it usually comes with a number. That number is usually found on the periodic table. But for this purpose I won't really get into that. I'll just talk more about electronegativity in respect to going down the group. So now, as you go down a group, the electronegativity actually decreases. Electronegativity decreases. So one of the reasons why it decreases, now remember that electronegativity is how willing an electron is to gain electrons. Now sodium is actually, compared to potassium, that electron in its valency shell is actually closer towards the nucleus compared to potassium. The electron in potassium is further, the valence electron in potassium is further out. So basically the electrostatic attraction is a little bit less of that electron there towards the center of the nucleus. And what this causes, it actually causes the electron to be more easily released. Okay, so it's actually easier for potassium to release its electron because it's that very small fragment bigger than sodium, and that final electron in the very last shell has less pulling strength towards the inner nucleus compared to sodium. So the electronegativity decreases. Okay, and as you go down a group, because the atom or the element increases in size, and therefore the electrostatic attraction is less. I mean, even if you look at the noble gases, you'll find that there's a very interesting thing that happens as you progress down the group. So you'll find that helium is actually incredibly stable as an element. When you go down the group, what ends up happening is that the noble gases down the group become more and more unstable, and they actually can begin to react. Now, we think of noble gases as unreactive, and they are generally unreactive when they're in between these few elements here. And that's because there's still the distance between the electron shells and the inner nucleus is still not as significant. So it's easier to control the outer electrons than, for example, these elements down here. So if I show you a demonstration of this, let's say we have a noble gas here, neon. And neon it's in group number, for the final group, but it's in, it has only 2 electron shells, and whereas xenon has 1, 2, 3, 4, 5 electron shells. So neon, one, two, 1, 2, 3, 4, 5, 6, 7, 8. So this is neon, right? Now, and xenon, I think it's Xn. Once you get to the elements lower down in the periodic table, you kind of don't use them. Okay, it's Xe. Xe, and it's got 5. One, 2, 3, 4. This is going to be massive. 5. So if you can imagine in xenon that the final electrons, I'm not going to draw all the ones in between, but the electrons in the very final shell, there's 8 of them. As is the case with neon as well. Now with neon, remember that there's positive forces in the center of the atom. So these outer shell valence electrons, the distance towards that nucleus is much smaller. The distance, however, of the xenon to those electrons, those valence electrons, are really far out. The diameter becomes incredibly large. And so what ends up happening with xenon and with other very large noble gases is that these electrons, they can actually, they are more easily lost. Okay, so whereas these electrons here are controlled, because neon is really gripping onto those electrons. It will not let them go because neon's very stable, and those electrons, well, this is a completed atom, it's a completed electron shell. There's no way those electrons are going to be very easy to let go of for neon. But for xenon, it's those electrons are less controlled because the distance from the inner core of xenon to the outer electron shell, the distance is actually much greater. And so this has, you can say that, remember that electronegativity for neon electronegativity is going to be very high. Well, you can't even speak about electronegativity in this situation because there is neither a desire to pull electrons towards it, nor is the desire to lose electrons. So the noble gases are sort of, in terms of the electronegativity, not the best example to use, but neon's going to have more control over electrons, and xenon is going to have less control. So with xenon, you could see xenon as less stable, and therefore whenever an element is less stable, it means that it's more reactive. Whereas with neon, neon is more stable and less reactive. So this was higher up. Neon is higher up in a group, xenon is lower down. So as that's another trend that we have to look at, is that as you go from the top of the periodic table to the bottom within the same group, the reactivity down a group gets larger due to larger number of electron shells. You could see that clearly in the neon and xenon examples. Xenon has more electron shells. Those electrons are going to be hard to control, and therefore xenon is going to become more reactive. Neon, on the other hand, has a good grasp of those valence electrons. They're really pulling towards the center, and as a result, neon is going to be less reactive. Now, going back to the electronegativity example, this actually, the reactivity also affects the electronegativity, because as the atom gets larger and larger and larger, it has more electrons in it to control, and therefore gaining electrons is going to be harder. It's going to be easier losing them, and so this will decrease the electronegativity. So one of the things that we find, which is very interesting, is that the most, if I go back up, we did cover a lot of content here, but as we go back to our periodic table, we actually find that fluorine just clean this up a little bit. that fluorine, which is here, it's actually the most electronegative element in the entire periodic table. Most electronegative. And so the reason why it's most electronegative, okay, so now as we did discuss this, as we go across the group, across the period, we find that we fill up more and more electrons in that shell. Okay, so we understand that fluorine, for example, has 7 electrons in it, and as a result of having 7 electrons in it, it just needs to it really wants to grab another electron to become stable, like neon. So we've established that as we go across the period, the substance becomes, the element becomes more electronegative. Now, if we look in terms of a group, the element at the top has high electronegativity, and the elements at the bottom have lower electronegativity. And the reason why is because fluorine, it only has 2 shells, and therefore those electrons in that second shell are really closely controlled by the nucleus, by the protons within the nucleus. But as we go, say, the atom gets bigger and bigger in the case of, say, iodine or some of these elements down here, because of the size of the elements, the electrons are further out and they're further away from the nucleus, and therefore they're more easily lost. Okay, so that has an impact. That essentially means that the element has a lower electron negativity, because remember that when electrons can be lost, that decreases the electron negativity. So fluorine, because its position, if you go across from left to right, it's on the far corner here, and it's the highest in the group. Fluorine is the most electronegative element in the periodic table. So it wants electrons the most, because one more electron will fill it up and will make it into a very stable element, and also because it's at the very top of the group, which means that the electrons are more, they have greater electrostatic attraction towards the inner nucleus.